Okay, everyone. So in the last videos, we talked about how we could use integrals to find areas of certain enclosed regions or lengths of curves. And now we're going to talk about one method of finding volumes using integrals. And so what I have here is this weird shaped volume. To me, it looks kind of like a Dr. Seuss musical instrument or something like that. Call it like Dr. Seuss's trombone. But what we can do if we want to find the volume of this weird shape, there's no, straight equation like the volume of a sphere is 4/3 pi r cubed, the volume of a cylinder is pi r squared times h. There's nothing, a formula like that that we can use to find this shape. However, what we can do is we can take an advantage of the fact that we can come up with a formula for the cross section at any given point along this shape. So the cross section is this yellow region, and we say AX is the area of that cross section. Notice that is a function of X. If I took a cross section at this point here or at that point here, I would get a different shape than this yellow shape. But let's assume that we had a function that told us what that cross-sectional area is. Well, what we could do is we could use that cross-sectional area and we could create a slice. This is why it's called volume by slicing. So if you really want to picture this, pause the video right after I say this, run to your kitchen. Hopefully you have a loaf of bread in there. Pull out a loaf of bread, and this is basically what we're doing. So you could estimate the volume of that loaf of bread by just counting up the volumes of each individual slice of bread. Now, for a loaf of bread, that's really easy because each individual slice has the same cross section. However, if they didn't have the same cross section, if all the slices of bread were different, like let's say, you go to the bakery section in Ingles, you can get those loaves of bread which are not kind of like perfect kind of rectangular shapes. They're a little bit oval-like on the ends. You'll notice that as you slice the bread, the cross-sectional area of each slice somewhat changes. So if we take a slice of this shape right here, that would look something like this. Okay, so do you guys see that right there? And actually, we'll draw a dotted line right there. So do you guys see the slice that's shown up right there? So if what we do, if we have this function for the cross-sectional area, if we know the thickness of our slice, which we'll call that thickness dx, we could figure out the entire volume of this shape by summing up the areas multiplied by that little thickness all the way from x equals a to x equals b. Well, that's the exact same as just doing a Riemann sum, but instead of doing it in 2 dimensions, we're doing it in 3 dimensions. So really, this thing right here, as you've probably thought by now, if we make that dx length really small, which is why we called it dx, remember d in front of something means teeny, teeny, tiny change. If we make that dx thickness go to 0, this sum becomes an integral. So in this case, we can say the volume will be the integral from a to b of our area function dx. So basically, as long as we can find some function that tells us what our cross-sectional area will be at any given point, if we integrate that function over our limits of integration, a to b, we'll end up finding the volume of that particular shape. Now again, this makes sense because think about units. The units of AX are going to be something like meters squared or feet squared. The units of DX, tiny change in X, those are going to be in units of meters. So if we multiply the two things together, we end up with meters cubed or the units of volume. Okay, so everything works out and everything's nice. All right, so let's look at a quick example of this. We can actually derive the equations on this slide and the next one for the volume of a cylinder and the volume of a cone. So in this case, let's take a look. We'll say we have a straight line. This black line right here is the line y is equal to r, so y is a constant. And the blue section represents, what I've made in blue is like our total volume, what that's going to look like. It's a cylinder, okay? So the red section is our cross section. So if you want to visualize what a cross section is, in this case, imagine I have a machete in my hand and I just chop this cylinder in half perpendicular to the x-axis. If you then turned around and looked straight down the x-axis, you would see this kind of circular shape right there. That's our cross section. Notice the cross section is perpendicular to the x-axis, okay? That's a detail that's going to be very important as we look at the next couple of slides. Okay, so if we want to find the volume of this thing, well, we know that the area of all these cross sections is going to be pi times whatever this radius of that circle is squared. Well, because the black line we drew right here represents y is equal to r, which is a constant, our radius is always going to be this value r. So therefore, if we want the volume, that's going to be the integral from 0, because we start at this point 0, 0, to the x value h. We go all the way to h, and our area is going to be pi times our function. And I'm actually first going to write this as pi times y squared dx, but our function y is equal to r. So if I replace that, I get 0 to h of pi r squared dx. Okay? So remember, r is a constant, pi is a constant. So if we evaluate this integral, this will be pi r squared x from 0 to h. And if we go through and solve that definite integral, it's just going to be pi r squared times h, which is indeed the volume of a cylinder. So we just derived that using the volume by slicing method. Okay. Now just keep in mind, I put this y in here simply to remind us that our radius, or our cross section is a circle, and our radius is dictated by this black line right here. Now in that case it was a constant, so it was very easy, but in the next page we're going to see how we can do this for something that's not quite as easy. Okay, so here we have a cylinder, all right? And again, notice that I've drawn a black line, which is going to be some particular function. In this case, the function is y is r over h times x. Now keep in mind, r is this y value right here, which is the same as that length, and h is going to be the total length of this cone. So why is this line y equals r over h times x? Well, we got to do the point slope equation. Realize that this is just a linear line. Its slope, rise over run, its rise is r, this value right here. Its run, this distance along the x-axis is h. So its slope is r over h. And since it goes to the origin, our point is 0, 0. If we apply the point slope formula to that, we're just going to get r over h times x. If that confuses you, then please write this point right here as x equals h, y equals r, and this point right here as 0, 0, and pause the video and you come up with an equation for that black line. I guarantee you will come up with y is equal to r over h times x. But it's very important you understand why I got to this, because when I've done this, this particular demonstration in previous years, students were totally blown away how I came up with the equation of that line. So make sure you understand that before you go further with this. Okay, so again, this red section is our cross-sectional area. Again, that's going to be a circle. If I take a machete and I chop this cone perpendicular to the x-axis, I'm basically going to chop it completely in half. And if I look at those two pieces, I'm going to see circles as those cross-sections, okay? Now, the circle, the radius in this case is going to change as I move along the x-axis. So that's why now it's a little bit different. Basically, our radius is going to be that height y right there. So if we want to figure out the volume of this, the volume will be the integral, again, from 0 to h, because that's where we're starting. That's the starting point and the ending point of when we're adding up our slices of the area of a circle. Now remember, the area of a circle is pi r squared, but in this case, again, it's going to be pi y squared, okay? So what we do is we plug in our formula for y. So this will be the integral from 0 to h of pi times r over h x squared dx. So if we rewrite this, we'll get the integral from 0 to h of pi r squared over h squared x squared dx, which if we evaluate that integral, remember, little h is a constant, r is also a constant. The only variable we have in here is x. So this is pretty much the same as just a constant times x squared, which would give us 1/3 that constant times x cubed from 0 to h. All right? Well, if we plug this in again and we evaluate this definite integral, we're going to get 1/3 pi r squared. And because we'll have an h cubed over h squared, that just reduces down to h. And hey, what do you know? That is the volume of a cone. Okay? So we've used volume by slicing now in two different cases to prove the volume of a cylinder and the volume of a cone. We could do the volume of a sphere as well, but it's basically just a repetition of this with a different function for the radius right there. Okay, so those were some examples of how we use volume by slicing. So why don't you guys look at this problem and see if you can solve this problem using volume by slicing. So pause the video. All right, so if you gave it a shot, some people might have trouble initially visualizing what this volume looks like. So it says that this shaded region is the base of a solid. So basically, if we covered a solid up with ink on the bottom and then stamped it on a piece of paper, this is what would come up. So we got to think of a three-dimensional image coming out of the page. But what it says right here is that the sections of the solid perpendicular to the x-axis are squares. Okay, so what that means is that if we take a section perpendicular to the x-axis, that is going to come out of the board as a square where all of the sides are the exact same as this red line right here. So what I went ahead and did for us is on the next one, I translated this into a three-dimensional image. Now again, the blue represents the outline of the volume. We still can see in here our black shaded region, and I've put the points on the x and y axis. And this time the red, again, represents the cross-section. If I took a machete and I sliced this volume perpendicular to the x-axis, we would end up no, not red. That's okay. We're too deep into the video now. We can't start over. I can't afford to do this again, okay? So anyway, yeah, we get that red shape. Hopefully you can make it out is a square. So that's what this means by the cross sections of the solid perpendicular to the x-axis are squares. Okay, so if you didn't get that, if you were totally confused by what this volume looks like, try to solve this problem again, knowing this is what it looks like and this is what the wording of that problem was saying. Okay, so hopefully you guys have tried this one. And what I'm going to do with this one is we're not going to go through and solve the integral. I'm just going to write the integral. That would represent this solid, and you can either solve it with FNIT or you can solve it by hand. But for right now, the most important thing is just understanding how to construct that integral. Hopefully we've had enough practice in the past of how to actually solve integrals. But if you want to go ahead and practice it, by all means do it. So anyway, in this case, our area, again, is going to be determined by one of the sides of this cross section. So realize that we had a function right here. Okay, so this side, this red line I just drew, is going to have a height of x squared. So if we look at that square in the cross section, it'll have one side of x squared. If it's a squared, if it's a square, the other side is x squared. So therefore, the area of x is going to be x squared squared, because that's how we find the volume of a square. It's one side squared, or it's going to be x to the fourth, all right? And let's get rid of the red ink now and then use black. So if we want the volume, that'll be the integral of, well, our limits of integration are again from 0 to 2. And this will just be our area function inside the integral, which is x to the fourth dx. And there you go. That's the integral which would give us the particular area of this thing. So pretty simple. So if we went through and evaluated it, we can actually do this one because it's so short. We would get 1/5 x to the 5th between 0 and 2, or 2 to the 5th over 5, which, would that 2 to the 5th, would that be 32? 32 over 5? Okay, well anyway, something like that. So that's an example of doing this one, okay? So you may think we're done. You may think this video is about to be over. Oh, no. Okay, we're going to show another example, and this is going to bring up something that I said would come up in the enclosed areas videos. Can you guess what it is? Well, now let's look at this problem. Read this problem real quick. What's different about it? There's a very small, minute difference, and that's now the cross sections of the solid perpendicular to the y-axis are squares. Okay, so now instead of having those cross sections be perpendicular to the x-axis, they're now perpendicular to the y, so they look something like this. So think about what we discussed in that video 2 videos ago about when we're doing things with respect to the y-axis and how that would change the integral that we use to solve this volume. So try to solve this one. Again, just write the integral. Don't worry about solving it. Pause the video, give it a shot. Okay, so again, if people were confused what this volume looked like, this one was a lot harder to draw. If you think that's a terrible drawing, well, you know what? Why don't you make the video, okay? All right, I'm here on my Saturday night trying for like 30 minutes to draw these three-dimensional shapes. It's not easy. Cut me some slack, please. So anyway, what we have in this case now is I have my y-axis right here. My x-axis is right here. I still have the point 2 and the point 2 comma 4. But now, again, this red section represents another square. And if I chop that red section perpendicular to the y-axis, again, I get a square. Okay? So in this case, my cross section is going to be dictated by this distance right here. So this distance is going to be a distance related to y stuff. So what we're going to have to do is convert this function over to y stuff, which gives us x is equal to square root of y. I need it to be a function of y now, not a function of x, because we are going to be integrating now along the y-axis instead of along the x-axis. And the equation of this line is x is equal to 2. So if we want to find the distance of that red line, that's going to be, if we want that, that will be 2 minus square root of y. Keep in mind, square root of y is this distance right here. 2 is this distance right here. So if we subtract, if we take this distance and subtract that distance, what we're left with is this distance, which is the one that we want, because that's going to be one of the sides of our squares. So if we want to come up with an integral for this, the volume will be the integral. Now remember, if we're integrating with respect to the y-axis, we need everything to be y values, okay? Even our limits of integration. So our limits of integration would be 0 to 4 because we're going from y equals 0 to y equals 4 right there. And now our area would just be this length, which we found before, squared, because if it's a square, we take one side, we square it, we get the area of the square. So this would be 2 minus square root of y squared dy. Remember, everything has to be y's, and there you go. That's the integral. We could go through and solve that, but again, that's something that could be useful for you on your own time, but in the instance of trying to make the video not way too long, we're not going to do that. So, like I said, volume by slicing, it's really not hard if you can just find a function for the cross-sectional area, but students still tend to have a lot of trouble with these problems, more so than with the next volumes we consider volumes of revolution. So battery's getting low. That's basically Steve Jobs telling me, wrap it up, you're talking too much. So come to class tomorrow with questions on this stuff, and we will go over example problems.